Hello everybody, it's Tarun. Welcome to your 7th tutorial in the Signal System and Control course. In this tutorial, we'll start with Unit 3, which is Fourier series representation of periodic signals. Okay, and what will this unit cover? First, before starting the Fourier series representation, okay, we'll start with the response of LTI systems to complex exponentials. Okay, this is something related to what we did in the unit 2. Okay, but it is more related to the Fourier series. That's why we are doing this in this unit instead of the unit 2. The second thing which we will do is Fourier representation of continuous time periodic signals, and the third thing is Fourier series representation of discrete time periodic signals, and the last thing in this unit will be frequency response of signals and some filters. Okay, so now let's start. Okay, so first start with what is Fourier series. Okay, it is a series which was defined by a engineer or scientist who was named Jean Baptiste Joseph Fourier. Okay, and if you want to know about him, you can go to this website and find out more about him. Okay, so now let's start with the frequency response of LTI systems to complex exponentials. So what is Fourier series? First of all, okay, it is a representation of periodic signals as a weighted superposition of complex exponentials. Okay, so till now what we have done, we have represented signals as weighted term of sinusoids or weighted term sum of cos functions. Okay, in the convolution sum and convolution integral terms also we did something like that. Okay, but Fourier series is representation of periodic signals as weighted sum of complex exponentials. Okay, in the case of continuous time, the complex exponential will be e to the power j omega t, and in the case of discrete time it will be e to the power j omega n. Okay, so now let's see why this is useful. This is useful because e to the power j omega t and e to the power j omega n are eigenfunctions of LTI systems. Okay, eigenfunctions are quite useful things when you know about them. Okay, but in this course you will not need anything about them. You just remember the name here. It will not be used afterwards. Okay, and it comes from the course linear algebra. Okay, so don't worry about it. For the continuous time LTI systems, we represent the Fourier series or the complex exponentials as e to the power j omega naught t will be represented as h of j omega multiplied with e to the power j omega t. Okay, and for discrete time LTI system, it will be e to the power j omega n will be represented as h of e to the power j omega multiplied with e to the power j omega n. Okay, so these complex constants h of j omega and h of e to the power j omega are called eigenvalues associated with e to the power j omega t and e to the power j omega n respectively. Okay, again just remember the name eigenvalues. So now let's see the proof. Okay, we know that the convolutions integral will be integral minus infinity to infinity h of tau x of t minus tau d tau. Okay, here we are taking x of t as e to the power j omega naught t. So if I replace x of t minus tau with e to the power j t minus tau d tau, okay, and when I solve this, then I can take out the e to the power j omega t outside, and the remaining term I can represent it with h of j omega. Okay, with the multiplication with e to the power j omega naught t, j omega t. Okay, so with the definition of this proof, we can say that h of j omega will be this. So will be this function within the box. Okay, similarly you can solve for the discrete time LTI systems. Okay, with the input x of a n equals to e to the power j omega n, and similarly you will get the answer where the eigenvalue will be e to the power h of e to the power j omega. Okay, keep in mind that two things, that there are two different things, h of j omega and h of e to the power j omega, where h of j omega is for continuous time and h of e to the power j omega is for discrete time. So now let's see the representation. Okay, so we have a continuous time LTI system and we are representing the input signal as x of t equals to sigma ak e to the power j omega kt. Okay, and the output signal obtained will be same, all things will be same, and we will just be multiplied with h of j omega k. Okay, so this you can similarly do for discrete time case, but here it will be h of e to the power j omega k. Okay, so this was the input and output relation within these things. Okay, so now let's see the Fourier series representation of continuous time periodic signals. We are taking a periodic signal with fundamental period t and fundamental frequency omega naught equals to 2 pi by t. Okay, where the input signal x of t is represented in this manner: summation k equals to minus infinity to infinity ak e to the power j omega naught kt, which can be represented in this form, where replacing omega naught with 2 pi by capital T. Okay, where ak can be find out with the help of this formula: ak equals to 1 upon t summation integration over the time period t x of t, and with multiplication there is a conjugate of complex exponential which was there in x of t. Okay, so 1 t is the fundamental period, you all know that. Okay, and these are the conjugates of each other. Okay, the complex exponentials related in this Fourier series. So now let's see the proof of this thing that we have done. Okay, we need orthogonality to prove this thing that I have told you. Okay, for orthogonality we require the term ak will be equals to 1 or say an, which we will see later. Okay, in this you can see that this will either be t or 0, represent depending on the value of k. Okay, so now let's see that x of t we put here. Okay, we are performing the integration. Okay, so what does happen? Okay, it happens that with the help of Euler's formula you can divide it into or say one more thing before the Euler's formula. We are using what then? If we are taking inner product of two variables, say a and b, then it will be integration or summation of a b conjugate, something like that. You can look out that in the vectors. Okay, but here what we are trying to do that if here in this function, okay, k equals to n, then the whole thing will be equals to e to the power 0, which will be 1, and you can remove the complex exponential term. If k is not equals to n, then k minus n will be an integer. Okay, and then it will be of the, and I can replace omega naught with 2 pi by capital T, and it will be of the form e to the power j 2 pi. Okay, it will be of the form that. So you can expand it with the help of Euler's formula now, and you will know that its value will be 1 always. Okay, so this function will be 1. Okay, and so we have now rejected this because I have told you how to reject this term, and the summation of ak with from minus infinity to infinity we have represented it as an. Okay, by rejecting this term we will get 1. Okay, rejecting or expanding. Okay, and integration of it over 0 to 2t we will get t, capital T, and capital T and 1 upon t will be cancelled out, and we will get an. Okay, so this is the shorthand notation for Fourier series, where x of t is the signal and a double-sided arrow, and over that arrow we write fs and the Fourier series coefficients. Okay, ak is the Fourier series coefficient or spectral coefficients. So this is the shorthand notation for Fourier series representation. Okay, thus this term a plus minus k, and it is over plus minus k j omega naught t. It is kth harmonic component, and a naught will be DC component, and plus minus 1 components are fundamental components. Okay, for a real signal, now let's see the relation between ak and a of minus k. So now let's take the conjugate of our input signal, which we have defined earlier. So when taking conjugate, we'll get this. So summation remains same, ak will be conjugated, and the complex exponential will now have minus j. Okay, and now I have replaced k with minus k, so this minus here will become plus here. Okay, and this minus will become positive here, and this k is represented with replaced with minus k. Okay, so if I compare this term with our input signal, which is this, so I can see that summation is same, complex exponential is same, and ak is different only. So I get that it implies that ak is equals to a minus k star. Okay, so now let's see an example. This is a periodic time function where x of t is 1 plus sin omega naught t plus 2 cos omega naught t plus cos 2 omega naught t plus pi by 4. Okay, so I can expand this signal with the help of sin omega naught t and cos omega naught t by expanding them in the form of complex exponentials like this. Okay, and after that we can combine all the complex exponentials like this. So this equation gives us the Fourier series coefficients of this input signal. Okay, so here we know that the complex exponential always contains a variable k inside it. So here you can see that the value of k is equal to 0 in this case, k is equal to 1, k equals to minus 1, k equals to 2, and k equals to minus 2. So we have 5 Fourier series components here, a naught, a plus minus 1, a plus minus 2. So their values will be a naught equals to 1, a1 equals to 1 plus 1 upon 2j, a minus 1 equals to 1 minus 1 upon 2j, a2 is equals to 1 upon 2 e to the power j pi by 4, and a minus 2 will be 1 upon 2 e to the power minus j pi by 4, and the other Fourier coefficients are 0. So ak equals to 0 for mod k greater than 2. So this is another periodic function which is exercise for you to calculate this Fourier series coefficients. Okay, you can calculate this Fourier series coefficient with the formula which I have told you earlier. Okay, and with the help of Fourier series coefficients we can plot two curves or two spectral graphs. Okay, the first one is mod ak with k, which is magnitude spectra, and the second one is angle of ak with k, which is the phase spectra. Okay, these spectra are very much important. Okay, because they will be used many times in this course, and there is a course also in electronics and communication engineering, which is principles of communication, and that course is wholly based on these type of spectra, how to plot them and how to use them. Okay, so the next example which I am going to tell you is a periodic square wave. So x of t is 1 for mod t less than t1 and 0 for t1 to t2, t by 2. Okay, so I can calculate the Fourier series coefficients. You have to calculate them yourselves with the help of the formula which I told you earlier. Okay, and we get this function of Fourier series coefficients. Okay, now I want to tell you one more thing which is very important, which I had also told you in the first tutorial, which is sinc function. Okay, Sinc function is of the form okay, sinc of x is equals to, or sinc of the variable will be equals to sinc of x, sorry, sin of x upon x, or sin of pi x upon pi x. So I can also represent this function or term with the help of sinc functions by multiplying 2t1 by t here, okay, and here. So I'll get the answer in the terms of sinc function. This sinc function is very important regarding the square waves, and its curve is also important. Okay, so this is the curve of sinc function, something like that. Okay, we'll see that in the later sections. Okay, we have plotted the magnitude spectra and phase spectra of this signal. So okay, I suggest that you try the examples yourselves. If you get any problem, you can go through the book to see more solved examples thoroughly. Okay, so now let's see the next topic, which is convergence of Fourier series. So why are we checking this? Because it is important to know that whether a signal can be represented with the Fourier series method or not. Okay, we know that periodic signal can have discontinuities. Okay, and in the Fourier series representation, we know that we are representing any signal with the Fourier coefficients, and the Fourier coefficients are discrete points, and we are making them as a continuous signal. So the signal contains infinite number of Fourier coefficients, which is discontinuities. Okay, so we earlier or till now we have learned about the infinite Fourier series. Now let's see the Fourier series in a finite manner. Okay, the finite Fourier series is represented in this way: x and t equals to k minus n to n summation ak e to the power j k omega naught t. Okay, this convergence is the mean squared approximation error convergence. Okay, and if I want to calculate its energy, okay, or energy of approximation error with the mean square error, En equals to integration over one time period xn of t minus xt of t mod whole square dt. Here this term xn of t minus xt square is a mean squared error. Okay, and for a class of periodic signals, which is, we know that finite energy, the periodic signal for over a particular time period should have a finite energy. So this is this, and when n tends to infinity, this En should tend to 0. This is the mean squared approximation error. Okay, what does it mean that En is not 0? En equals to 0, it does not imply that xn equals to xt for every value of t. Okay, and the difference between xn of t and xt of t has 0 energy. So this was the mean square term which I told you. Okay, and the second convergence conditions are Dirichlet conditions. Okay, what are the Dirichlet conditions? That first condition is that for one time period, the signal xt of xt must be absolutely integrable. Okay, this is the meaning of absolute integration, that mod xt dt for one time period should be less than infinity, and the xt signal should have finite number of maxima and minima in a particular time period, and it should have finite number of discontinuities in one time period. Okay, if the Dirichlet condition satisfy, then xt is equals to Fourier series representation. So x and t, limit n tends to infinity, will be xt. Okay, there is a constraint in that it is not correct at the isolated values td. So what are these isolated values? You can calculate them with this formula: limit n tends to infinity, x and td, x of td plus x of td minus upon 2. Okay. So the last topic which I am going to teach you in this tutorial is the Gibbs phenomenon. Okay. So Gibbs phenomenon is something used for approximation. I want to tell you that a square wave cannot be generated ideally. Okay. What is actually a square wave? A square wave is a summation of large number of sinusoids. Okay. When we sum large number of sinusoids, then they compress together and form a structure like square waves or rectangular waves. Okay. But we cannot generate a ideal rectangular wave with sharp edges. Okay. So we have a signal x and t. Okay. And when we are increasing our value of n, the signal is starting to compress more. Okay. It is starting to flatten at the middle and something more at the corners. Okay. So this is for 4 values of n and this is for 99. You can see that it is starting to feel something like square wave, and if we increase the value of n more, then we will get somewhat a square wave. Okay. So this is what Gibbs phenomenon tells us. Okay. In the next tutorial, I will teach you the properties of continuous time Fourier series and discrete time Fourier series representation. So thank you guys for watching. I will see you in the next tutorial.